I want to talk for a few minutes about Ethernet frames, the topic for this week. And I've got the ebook, section 2.1, Ethernet and IEEE 802 local area networks or LANs. And section 2 deals with a lot of different LAN technologies. I want to focus on Ethernet being really the most important one and the one you're really going to run into most often. Now, Ethernet, Ethernet carries data in what's known as an Ethernet frame, right? And as you probably guessed, Ethernet frame has a certain structure, a certain way that the data in it is organized. And with Ethernet, it's kind of an interesting story because you've got a number of different Ethernet frame types. Now, in the article. In the ebook, it talks about this. Let me recommend actually that you take a look at the Wikipedia article on Ethernet frames. I think that's or Ethernet frame singular is what I looked up. And it has a pretty good description of, again, what an Ethernet frame looks like. And also, kind of a confusing issue with Ethernet frames is that there's actually more than one Ethernet frame. And maybe the short version of the story. You probably, in your first networking class, you talked about the IEEE 802.3, and you probably know that as the Ethernet standard. You got to be careful when you're talking about Ethernet frames, though, because there is an IEEE, or at least an 802.3 standard. Let me not use the word standard. There's an IEEE 802.3 version of the Ethernet frame, which is not standard, which does not fit the 802.3 standard. Here's the story, a little bit of more interesting computer history, and you've probably run into this before. Situation where a large company will come in and say, great, there's a standard, but we're going to create our own standard, right? See also Microsoft and IBM back in the day when they were the huge company in operating systems or hardware, and there might be standards out there, but they decide, no, this is how we're going to do it, and we're the dominant company in the field right now, and whatever we say goes, okay? In this case, you got to blame Novell, right? If you've heard about Novell was a company back in the 90s. Novell NetWare was really, really huge. Novell came up with, I can't remember what the idea was. The bindery? I might have to look that up. Which everyone says Microsoft stole, and they called it Active Directory. This whole idea that everything on your network is maintained in a database, user accounts and what machines are using and what your infrastructure looks like, and Novell came up with that. In any case, back in the 90s, Novell was really, really big, and they created an Ethernet standard, and they called it the 802.3 standard, except that it didn't actually match the official IEEE 802.3 standard. So you see, actually, in the Wikipedia article, there's let's see where, yeah, the Novell, sometimes it's called the RAW, Novell RAW 802 or IEEE 802.3 non-standard variation frame. Okay, so there's that floating around. Then there's also the IEEE 802.2 LLC frame, and there's the 802.2 Subnet Access Protocol, or SNAP frame, and then there's the Ethernet 2 frame, or Ethernet version 2, or DICS frame, as it's sometimes called, which actually is the most common one that you see used anymore. So the story now in the 2000 teens is actually a lot clearer because most everything's using Ethernet 2. However, if you're running some legacy systems, and people still do, running Novell, it might be running an 802.3 raw frame. LLC and Snap you still see occasionally, but not nearly as often. So I guess the story is, you go back into the 90s and the early 2000s, there were issues with different frame types floating around. And really, once upon a time, Microsoft and Novell machines could not communicate because they used different frame types. What you had to do is you could eventually tell your Microsoft machine to use an IEEE 802.3 raw Novell frame, or you could tell your Novell to use like an Ethernet 2 frame or Snap frame that was running on a Microsoft machine. In other words, you had to switch them back and forth. Eventually, you could get to the point where you could tell your devices to auto detect. So whatever frame came at them, they could figure out what kind it was. But for a while, there was a big incompatibility problem. Nowadays, like I said, it's mostly come down to Ethernet 2, and that's really what we're going to talk about. But I am going to say a few things about how you tell the difference. So let me scroll back up to the top of this article because the Wikipedia article has a really nice drawing of the 802.3 Ethernet packet or frame structure. And this is pretty standard all the way across. And so let's go into this kind of field by field and just talk about what these fields are for. At the beginning, there's a preamble and start of frame delimiter. Sometimes that's called SOH, start of header. Sometimes you see it listed as just SOH, the start of frame delimiter. Now, what those are, and let me see. I'm wondering if I want to get maybe a notepad up here just so I can do a little scribbling for you. What those are, the preamble in hexadecimal looks like this. 2, 3, 4. All right. Now, remember from studying hexadecimal, all right? You can convert a hexadecimal number into a binary number. When you do it, each hexadecimal digit becomes a 4-digit binary number, okay? So this A is 4 digits and this A is 4 digits. Altogether, that's 8 digits, right, which is a byte, okay? So what I'm getting at is that represents 1 byte of data, right? 4 digits and 4 more digits. Okay, so what I've got here, and usually when you see hexadecimal written out, you see it in groups of 4 hexadecimal digits with a space, and that's just to make it readable. So this is a byte, that's a byte, those two are a byte, those two are a byte, another byte, another byte, another byte. In other words, 7 bytes. And if you see over here, 7 octets, aka 7 bytes, right, that is what the preamble looks like, and the preamble always looks like that. Okay, now, what that looks like in binary. Remember that the hexadecimal digit A is 10, okay, which in binary is an 8 and a 2. Okay, so it's 1 0 1 0. All right, so realize now what you've got here is basically this sequence of 1 0 1 0 1 0 1 0 1 0 1 0. Oh, actually that's not correct because I left out 1 0 1 0 1 0 1 0. 1 0 1 0 1 0 1 0. That's a byte. Here's another one. Okay, here's another defense of why we like to write things in hexadecimal, because they're shorter than if you write them in binary. Okay, but that's it. That's the sequence. And obviously, it doesn't do much. It's obviously not carrying any data. So what is it for? All right, let me drop a couple concepts on you. Asynchronous versus synchronous. All right. Asynchronous transmission, I should say, asynchronous transmission is a way of transmitting between two devices where the devices are always synchronized. All right, now what is synchronized about? You got a network interface card on your computer, okay? Data is coming into that network interface card. That network interface card has to know where the beginning and ending of every bit is located so it can successfully read it, right? You remember looking at NRZ, NRZI, Manchester encoding signals. They were highs and lows, up, down, things like that. Obviously, if you have a signal, high and then low, if you're not reading it in the correct space, it's possible to misread it. It's possible to read a high signal as actually a low, or in other words, what should have been a 1 turns out to be a 0. So what has to happen, and usually the way this works is the network interface card synchronizes itself to the incoming signal. Right? There's nothing that keeps there's nothing separate that keeps the timing between the sender and the receiver the same. It's just the sender sends a signal and the receiver sees that signal coming in, and based on when the signal goes up or goes down, the reader, the receiver, can adjust its timing on its network interface card until it actually can successfully read that correctly. All right. Now, ways of handling this. One way, asynchronous, is that we constantly keep that receiving device synchronized to the incoming signal so that we're constantly sending something. And usually the way this works, this was kind of typical on older, I don't want to say older necessarily, but mainframes and mini computers where you had terminals hooked up to them. And so what actually happened is if you pressed a letter, like let's say you pressed the capital letter A, which in binary, in ASCII actually, is 01000001. I just happened to remember that one. Okay. So what would actually be sent, as soon as you hit the letter A, it would send that binary code from the keyboard on the terminal into the actual computer, right? And when it would try to display A on the screen, it would send that binary signal back to the terminal, and the terminal would display it up on the screen. Now, the way it did this is that right before it would send that, it would send what was known as a start bit, which is usually 1. Okay, and then at the end of that letter, it would send a stop bit, which is usually also 1. Okay, so for the letter A, what you'd send, sorry, I got those backwards. Those are both zeros. Okay, sorry. Start bit and stop bits usually, you can change it, you can have it different ways, but usually it's 0. So what happens is when you send the A, you send a start bit, then the data, 01000001, and then a stop bit. Okay, now the trick is that all the time that you're not sending data, and realize that with asynchronous, usually what happened is you hit a letter on the keyboard, it sent that letter. You hit another letter, it sent that letter. In computer time, a typist, even the fastest typist, is incredibly slow. So what happens is you hit a letter, and then as far as the computer's concerned, there's this enormous amount of time before you hit the next letter, right? So during the time between one letter and the next letter, the computer or the dumb terminal would be sending to the computer what's known as idle bits. All right, and idle bits are usually 1s. All right, so you can imagine what's going on. Nothing's being typed, right? So my dumb terminal is sending 11111111111. All right, and then I hit the letter A. Okay, then it says, okay, start 01000001, stop, and then back to idle. Right. And as long as nothing else is going on, it keeps sending idle. And then I hit the letter B. 0 is a start bit. 01000010. Stop. Back to sending idle bits. Okay. So that's basically how it works. So what happens then when you're not actually sending data, you're sending 1s. Now, this works very closely with NRZ I, if you remember that from your reading. NRZI would have 0 represented by no change in the signal. Right, but remember that 1s means you change the signal. Right, so what's happening during the idle part? Well, every 1 means change the signal. In other words, go low to high or high to low. So basically, when nothing's being sent, you're getting low, high, low, high, low, high, low, high, low, high, back and forth, right? And what that's doing is that's changing that signal. Remember that square wave signal, and the receiver is keeping synchronized to that incoming signal. So the receiver is keeping synchronized all the time when no data is actually being transmitted back and forth, just a bunch of idle bits. When you actually have data, you have that start bit, which is a 0, the data, and a stop bit, which is a 0. And the worst that could happen is you could have 10 zeros in a row, right? Over the course of 10 zeros, your receiver is not going to get out of synchronization. And then when the 10 zeros have been sent, then you're back to sending 1s again, so you resync. Okay, so that's the basic idea of asynchronous transmission, is you always stay synchronized. But like I said, that's typically used on dumb terminal to mainframe kind of computer setups, and it typically uses NRZI as the actual signaling technique. The problem with that is if you can imagine a room full of computers, all hooked up to a switch or a hub, right? Would that actually work if they were using synchronous transmission, right? So if they were all sending data at the same time, in other words, when nothing was being sent, they're sending data. They're sending ones. They're sending idle bits, right? Realize, of course, what's going to happen is all those idle bits are going to collide on the network, and you're not going to be able to send any data. The trick with local area networks is when there's nothing to be sent, nobody sends anything, right? You're totally quiet. And then when you want to send something, then you send it, and then you go back to being quiet again, right? So there's nothing going on the network when there's no data being sent. Realize with asynchronous, you're sending ones all the time when you're not sending data. All right, so synchronous, and these names are seem kind of backwards. Synchronous transmission means that your network interface cards are not synchronized all the time. You have to do something to synchronize them. Okay, that's where this preamble comes in. Right. So once again, in the preamble, we've got 7 bytes of just AA, right, which is a 10101010. And maybe you could imagine what's going to happen there is basically you got this on-off, on-off, on-off signal going on. So what happens is this signal is traveling down a wire and arrives at your network interface card, right? The clock on your network interface card could be anywhere, right? All of a sudden this data starts coming in. And again, your network interface card is going to start synchronizing itself to the changes in the signal, when the signal goes up or when the signal goes down. Those changes. So it's adjusting its clock, it's adjusting until it can successfully read the incoming signal. Realize that when that 1-0 stream starts coming in, your network interface card its clock might be so far off that it's going to incorrectly read that incoming data for a little while. All right. So the idea is this signal starts coming in, and, who knows, maybe about right there, I get my clock adjusted and I'm reading the rest of it in successfully. Okay? So I don't necessarily read in correctly from the first bit. It may take a couple bytes before I get my clock adjusted, right, so that the data is coming in successfully. Now, here's the problem. I am now successfully reading in the data. Where am I? Right? I am somewhere in the midst of the 7-byte preamble, but I don't know where, right? I'm seeing this 101010 sequence come in, but I don't even know where the byte boundaries are at that point. I'm just successfully reading in ones and zeros. So I've got to have something that marks where the end of the preamble is located and where the beginning of the other important stuff is located. All right, that is the start of frame delimiter. Okay, again, I mentioned sometimes it's called a start of header. All right, it is 1 octet, it is 1 byte long, and it looks like this. It's A, B. All right, and so in binary, what that looks like, A, again, 1010, and B is 1011. Okay, that's the trick. So down at the end of the preamble, you have this start of header. So you got this 1010101010 coming along. Right, your NIC finally starts reading this incorrectly, and all of a sudden there's a 1011. Your NIC now knows, I just hit the end of the start of header. The very next thing is the destination MAC address. Okay, so the preamble is used for synchronization. The start of frame delimiter or the start of header is used to basically tell the NIC you are now at the end of that preamble. The next thing, the next bit you see is the beginning of the MAC, the destination MAC address. Okay, so there's the story of the preamble. In some formats also, the entire 8 bytes are referred to as a preamble. So you might see drawings with preamble and start of frame delimiter, or preamble and start of header, or you might see drawings of just preamble and the whole thing's preamble. All right, next thing, MAC destination or destination MAC address. That's your 6-byte address burned into a network interface card. Right now, hopefully you hit that in networking somewhere. Remember, there's 2 parts of it. It's usually split in half. Part of it is like a manufacturer's number. Part of it is a unique number by the manufacturer. Some network interface cards are programmable, but for the most part, you get a totally universally unique destination or address burned into your network interface card. So the destination MAC address is where this frame is going. The MAC address is where it's going. And the source MAC address is, of course, where it's coming from. All right, now, okay. This is, ignore the man behind the curtain. Ignore this, the 802.1Q, which is optional. I didn't notice that even in this drawing. Just put some white out on your screen or something so you don't see that. Okay, because the next thing I want to take a look at is the ether type or length. All right, notice they've listed here ether type for Ethernet 2 or length for IEEE 802.3 as well as some of the other types. Here is the deal. When this was originally created, when the Ethernet frame was originally created, these 2 bytes, this 2 octet field, was a length. Okay, told you how long the payload was going to be. All right, now that worked for the Novell RAW IEEE 802.3, the IEEE 802.2 LLC, and the 802.2 SNAP. Okay, so it is what I'm getting at is it is a length if it is one of those 3 types. Okay, it is a type if it is Ethernet 2, and by type, what it's telling you is what created the payload. Okay, at this point, common types that you're going to see are IP, if IP creates the data payload, or if ARP or RARP create the data payload. Okay, there are a lot of other ones, but those are the ones that you're going to see at this point in the class. Now, how do you know the difference? Okay, here's the trick. Go over to the payload. Notice that the payload itself can be anywhere from 46 to 1,500. We have 1,500 bytes. Okay, so the maximum data payload is 1,500. Now, wait a minute. Let's go down. Yeah, okay. Let's look at this drawing, which is a little bit further down. It's actually in the Ethernet 2. And the reason for looking at this drawing is that it doesn't have that optional 802.1Q tag, okay, which kind of messes up the computation. All right, so look at this data, 46 to 1,500. Okay, that means the entire Ethernet frame has a 6-byte destination MAC address, 6-byte source MAC address, 2-byte ether type or length, and down at the end you have a CRC checksum of 4 bytes. Okay, that's 6 plus 6 is 12, 2 more is 14, plus 4 more is 18. Okay, so what you get then is that the entire Ethernet frame can be anywhere, and of course the number's right here, but I was showing you how to compute that number. The Ethernet frame is anywhere from 64 bytes to 1,518 bytes. All right, now let me find my calculator. Okay, and let me pull it over here. 1,518 in decimal. If I convert that into hexadecimal, I get 5 EE. Or if I want to write that in byte format, 2 hexadecimal digits for each byte, 05 EE. And 05 EE is the number to remember. I'm going to put it in here. All right. I'm sorry. 05 EE. Okay, is the maximum length of an Ethernet frame in hex. Okay, all right. So the significance of that number is that in the frame, and maybe I can go back up to this one. In this 2 octet here, or here in the ether type, if the number in there in hexadecimal is 05 EE or less, it's a length. Okay, so the point of figuring out this number in hex is that is the maximum length you could possibly have in an Ethernet frame, 05 EE. Okay, so anything 05 EE or less means this is a length, and means that your Ethernet frame type, whoops, just to click something, your Ethernet frame type is either Novell RAW 802.3, 802.2 SNAP, or 802.2 LLC. It's one of those 3. So if that 2-byte field contains something greater than 05EE, right? That means it's a type. Okay, and the trick is that when they came up with all the type numbers, they made sure that all the type numbers were greater than 05EE. For example, 0800, and that's in hexadecimal, 0800 is IP. Okay, 0806 is ARP, RARP, okay, which is going to be a common one that you see. Okay, those are all in hexadecimal. And by the way, if you ever see anything written with a 0x in front of it, that means it's hexadecimal. And maybe I get into that habit here. OX is not part of the number, just OX is an indicator that the thing's in hexadecimal. Sometimes you see that with data dumps or packet captures and things like that. You'll see a 0x at the front of it. Okay, so that just means this number is hexadecimal. Instead of being 800 or 806, it's actually 0800 hexadecimal. Okay, so 05EE or less means it's 802.3 raw, it's SNAP or LLC. Okay, greater than 05EE is going to be Ethernet 2. So that's most likely what you're going to see. And in fact, this little chart here, the Ethernet frame differentiation, kind of gives you some information, although the number that they're using, I'm not sure where they're getting that from. Well, and actually, keep in mind what I'm looking at. I am ignoring the preamble and start a frame delimiter, which you usually do, because you never know how much of that you actually read in. So it's usually not counted in the overall size. So notice the size includes the MAC, destination MAC address, source, the 2-byte type or length field, the payload, and down here the frame check sequence, which is usually 4 bytes. Okay? All right. Now, from there, how do you tell the difference? Well, what happens is inside the data payload, there's different initial frame elements that show up. And so what you do is look at the first 2 bytes of the payload. If it's Novell RAW IEEE, it's always going to be FFFF, right? If it's 802.2 SNAP, it's always going to be AAAA. And if it's LLC, it's going to be something else. So what I'm saying is, you look at the data payload, you look at the first 2 bytes. If it's all Fs, it's raw, Novell RAW. If it's all A's, it's SNAP. And if it's anything else, it's other. And I think somewhere in the article it said something about there's a possibility that an LLC could have an AAAA or an FFF at the beginning, but it's not terribly likely, so you don't usually run into that problem. Also, realize that Ethernet 2, since it's using those 2 bytes as a type, that means that it doesn't have anything that tells you the length. Realize, of course, that having the length there tells you how big the data payload is going to be, because although the destination MAC, source MAC, Ethernet type, and the CRC checksum, or the frame check sequence at the end, are all set lengths, fixed lengths, the data can vary in length, so you need something in there to tell you how long it is. Usually what you've got then is inside the data payload something that says this data payload is whatever length, right? So you don't have to worry about it in 802, or I'm sorry, in Ethernet 2. A length will show up there somewhere. All right, a couple other elements that you're going to see. The data payload, again, is anywhere from 46 to 1500 bytes, right? Giving you a total overall size of 64 to 1518. And finally, at the very end, you got the frame check sequence, which is always a 4-byte sequence. Maybe in another video, I'll show you kind of a short example of how that works, but that is used for error checking, right? The frame check sequence is used in a computation that if, basically, if it comes out to 0, I'll show you why later. If it comes out to 0, everything's okay, and if it comes out to anything else, that means somewhere in there a bit has been changed. Frame check sequence, by the way, is the name of the actual field. The CRC is the actual protocol that you use to compute the value that you put in that 4-byte field. All right, so that when you check that, it's not going to tell you exactly which bit is wrong, but it's going to tell you that some bit is wrong. And of course, realizing that some bit is wrong means that you've got to throw the whole thing away, right? Because you don't know if the bit that's wrong was in the payload. You don't know if the bit that's wrong was in the source or the destination or source MAC. You can't be sure where the thing is going. You can't be sure where it came from. You can't even be sure of the type of data it's in there, because you know at least one bit somewhere is wrong. Okay, so you usually have to throw it out. And it's significant to remember also that it gets thrown out down here at the Ethernet level, which is, remember, your models again is down there at the network access level, is where things get checked for errors and get thrown out. I've got more to say about that in a future video as well. Okay, so that's the basic idea of Ethernet frames. Again, you might want to go over, not only look at the ebook, but you might go over to Wikipedia also, because I think the drawings and explanations are a little bit easier to work your way through.